Hi, we're continuing with cell biology and life science in a nutshell. We were learning about the bilayer of a cell membrane, which is made up of phospholipid molecules, which are amphipathic, which means they contain properties of polarity on one end, on the head group where it's solid red, and non-polarity at the hydrophobic fatty acid tails, which is the light pink tails. So two fatty acid tails come off the polar hydrophilic heads. The head is comprised of a glycerol molecule bound to a phosphate as well as an alcohol group. So that makes it polar. And the tail is just two fatty acid chains. Usually one is saturated and one is unsaturated. So we're learning about, this is what it looks like, close up, the molecule. Phosphate, alcohol group, and glycerol backbone, and the two fatty acid tails, which make it hydrophobic. This is the saturated, this is the unsaturated. Unsaturated has a double bond in the middle of the chain between two of the carbons. So based on the structure of the phospholipid molecule, the bilayer forms into its shape because it is more energetically favorable for the hydrophobic tails to attract one another and the hydrophilic heads to turn away from the hydrophobic parts. So it just spontaneously forms into this kind of orientation. So similar ends of the molecule attract. So the hydrophobic attracts into the inner part of the bilayer, and the hydrophilic ends are on the either side where the water is. So this, it could be one side on the outside of the cell, extracellular fluid, and one on the inside of the cell in the intracellular fluid. Also here you have two aqueous compartments, and in an experiment they show that membranes can be measured as to how permeable they are when they make synthetic membranes, also called black membranes. And they make synthetic lipid bilayers. In other experiments, they study phospholipids molecules in the synthetic bilayers, and they label the lipid molecules in the bilayer using spin label resonance by adding a nitroxyl group, for example, a nitrogen oxygen group, which contains an unpaired electron, which is detected as a paramagnetic signal by the electron spin resonance spectroscopy. This way, the motion of individual lipid molecules can be studied and detected by the labeling of the polar head group of the lipid molecule containing this kind of spin label. So this is called nuclear magnetic resonance when you label a molecule. So again, the motion and orientation of a spin labeled lipid in a bilayer can be deduced from the ESR, or electron spin resonance spectrum. Such studies show that phospholipid molecules in synthetic bilayers very rarely migrate from the monolayer or leaflet on one side to that on the other. This process, known as flip-flop, occurs less than once a month for any individual molecule. In contrast, lipid molecules readily exchange places with their neighbors within a monolayer, 170 times per second. This gives rise to rapid lateral diffusion with a diffusion coefficient of about diffusion coefficient 10 to the 8th centimeters squared per second, which means that an average lipid molecule diffuses the length of a large bacterial cell, which is about 2 micrometers, in about a second. These studies have shown also individual lipid molecules rotate very rapidly about their long axis and that their hydrocarbon chains are flexible. So in the diagram, you can see that rotation occurs, flexion occurs, lateral movement of the molecules. However, flip-flop across the bilayer rarely occurs. So this shows the phospholipids' mobility is such and the types of movement that are possible for phospholipid molecules within the bilayer. Similar studies have been performed with labeled lipid molecules in isolated biological membranes and in living cells. The results are generally the same as for synthetic bilayers, and they demonstrate that the lipid components of a biological membrane in a two-dimensional liquid in which the constituent molecules are free to move laterally. In synthetic bilayers, individual phospholipid molecules are normally confined to their own monolayer of the membrane, mainly in the cytosolic monolayer of the endoplasmic reticulum membrane. For example, if none of these newly made molecules could migrate reasonably promptly to the non-cytosolic monolayer, new lipid bilayers could not be made. So the molecules move about readily within across different bilayers, whether the ER or the cells bilayer. So the problem is solved by a special class of membrane-bound enzymes called the phospholipid translocators, which catalyze the rapid flip-flop of phospholipids from one monolayer to other. So the fluidity of a lipid bilayer depends on its composition. The fluidity of cell membranes has to be precisely regulated. Certain membrane transport processes and enzyme activities, for example, cease when the bilayer viscosity is experimentally increased because of a threshold level. The fluidity of a lipid bilayer depends on both its composition and temperature, as is readily demonstrated in studies of synthetic bilayers. A synthetic bilayer made from a single type of phospholipid changes from a liquid state to a two-dimensional rigid crystalline or gel state at a characteristic freezing point. This change of state is called a phase transition, and the temperature at which it occurs is lower, that is, the membrane becomes more difficult to freeze if the hydrocarbon chains are short or have double bonds. So this shortness or double bond aspect of the phospholipid molecule makes them less rigid. It makes them less likely to freeze. So it adds, the more polar, obviously, the shorter the fatty acid tails, the more polar the molecule and fluid.